43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489,856,000. That is a gigantic number. Some of you may know where this particular number comes from, and others might not, but this is actually the number of ways to scramble or mix up a Rubik's Cube. You may wonder, how in the world has someone just came out with this number of the ways to mix up a Rubik's Cube? But there is a mathematical way to work it out. So if you consider a standard Rubik's Cube, there are 6 center pieces, or centers. There are 8 corner pieces, or corners, and there are 12 edge pieces, or edges. But a thing to consider is that the center pieces are actually there to keep the whole cube in place. The only really movable pieces are the corners and the edges. So we'll just call these the movable pieces to make things easier. So there are actually only 20 pieces that physically move. Everything just rotates around these center pieces. So we'll start by working out the permutations, or ways to arrange the corners. So as I said before, there are 8 corner pieces. So 8 in total. And if you're familiar with maths, if you, for example, wanted to work out if there were 4 people, let's say, and these are 4 chairs, then how many arrangements could these 4 people be sitting in these chairs? Well, the way to work that out is just to multiply these numbers. And this is known as 4 factorial, or 4 by 3 by 2 by 1. So this can be applied to a Rubik's Cube. So the corner pieces, there are 8. So the number of positions, or number of ways to arrange the corner pieces, is simply 8 factorial, or 40,320. That's what 8 factorial is. Now that's the number of ways, like the different positions that the corner pieces could be in, but not the different ways they can be twisted or oriented. So since there's 3 colours, that just simply means that there's 3 ways for it to be oriented. Now you may think that it's 3 factorial, but it's not 3 factorial, it's just 3. Because, for example, the corner that I've drawn over here, this yellow and this red, they can't switch pieces. They can't switch positions. The whole corner would have to rotate. You can't simply swap 2 stickers on that corner. The whole corner would have to rotate, so either yellow's on the top, red's on the top, and blue's on the top. So that's 3. So there's 3 arrangements for the orientation of the corner. So to find the value for the number of permutations of the corners, then all you do is 8 factorial and multiply that by the 3 from before, but the 3 must be to the power of 7. And there's a reason for that number 7. Since there are 8 corner pieces, if you solve 7 of the corner pieces, the other one has to be solved. There's no other place it can be. So you take 1 away from that 8, so it's basically 3 to the power of that 8 minus 1, or 7. And we'll work that out, and this is our value for the permutations of the corners. So now we'll do the edges. So there are 12 edges. Just like we said, there were 8 corners. There's 12 edges. So we'll work that out with 12 factorial, like from before. And 12 factorial works out to be 479 million 1,600. That's what 12 factorial is. And on these corner pieces, there were 3 different colours on the piece, but on the edge pieces there are only 2 different colours. So then the possible orientations of the edge pieces is 2, not 3 like the corners. So easily, just like the corners, what we'll do is we'll multiply that 12 factorial, and we'll multiply it by the 2 from before, but also just like we did 7 here, because that's 8 minus 1, we'll do 12 minus 1, which is 11. And that's just for the same reason. If you solve 11 edges, the 12th edge just must be solved. So this is our arrangements for the edges. So we've got the corners and we've got the edges. So let's just write that out as a formula. So it would be, this is for the corners, it would be 8 factorial by 3 to the power of 7. And we'll multiply that by 12 factorial by 2 to the power of 11. Now, you may think that's us finished, but there's one last step. Some of these positions that we're including in the total we'll get from this formula, they're impossible positions on a Rubik's Cube. Because you can never ever have a cube with only 2 pieces switched. So what we've calculated here using this formula, it includes all those impossible positions. So the last step is just to divide our total by 2. Or you can also write that as just multiplying by 0.5. And if you were to put that formula into a calculator, it would give you the correct total that we have at the very top of this page, which is 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489 million, 856,000 possible permutations. So I hope I explained that well and that you understand that. So just thanks for watching, I guess.